intrusive into the problem that we're faced with trying to this new evolution therapy for a needle. Design criteria, the specs we have to follow, the design evolution, the two ideas that we came up with to use the needle, and project management who worked on what in the project. So basically, the problem we're faced with is in conventional infrared therapy, the needle goes straight onto the skin. So with the needle, it can pass the skin because the skin blocks about 50% of the effective light that helps heal the joint pain and fat reduction, etc. So this can also in effect go to deep areas if you use a bigger needle. Also the problem for the design criteria is a 27 gauge needle, which is very small. It's about 0.4 millimeter hole. So you have to get the needle from the light through that. And we wanted to get 75% of the output power from the laser and use a wavelength of 700 nanometers to 2000 nanometers and pulsate at 1,000 hertz. So our first idea was with fiber optics. So we researched it, came up to be, we thought it could be a very good idea, but consider our budget was about 4,000. The diodes and the whole wiring of it is about 3,000 upwards. We didn't have enough money to use it. So we came up with our second idea, which is a collimating tube assembly with lenses. So basically it consists of the collimating tube, the lens. So this was much cheaper. The tube was about $300 and the lenses were, one lens was about $80. So basically for the project management, Boris and Gord both focus on focusing the laser with the tube and the lenses, lots of testing. Boris worked on the needle locator, designing in SolidWorks and CAD. He also worked with the machine shop, talking to them, communicating with them on both parts, and also the outside machine shop, which didn't work out. We still communicated with the bunch, and the final testing. So as stated, we're also focused on the laser focusing part mostly, also designing the collimating housing for the tube. Noel worked on electrical circuit in the box. Basically did everything for the circuitry, electrical, and the programming for the pulsation, and the final testing with Boris. And then I worked on helping with the electrical circuit, the handheld device, and 3D printing parts.
Okay, so we're going to go over the technical description. The tech description is broken into 3 parts. The components, we're going to talk about the assembly and also how it works. And the components are broken up into 3 parts themselves, the electrical, the optical, and mechanical / locating. So this is the electrical part. It's just used to supply the voltage to the laser, as well as it creates the 1 kilohertz pulsation. So it does this by using an electronic switch called a MOSFET. Basically, I program the Arduino to send a signal at the correct frequency, and it just opens and closes the gate at the required frequency. Right here you have a voltage regulator. This is just, it drops the voltage from the input voltage, which was 7.5 volts, which was required to power the Arduino, and as well to boost the signal of the on-off portion for the switch. So it needed to drop that signal, 7.5 volts, down to about 2.4, 2.5 volts, and that's what the voltage regulator is for. We also use some capacitors and stuff just to clean the signal. It improves the life of the laser diode. And Boris will be talking about, or Gord will be talking about this.
All right, so first we have the laser diode, which we had an output of 250 milliwatts because it was the one given to us by our industry partner. The wavelength is 980 nanometers, which is sufficient in the near-infrared range. It was a divergent beam, which meant we had to take it from being a barcode to collimating it with the collimating tube, which we bought in the range for the same range as the diode itself, so that it worked effectively. It takes the diverging beam and makes it a cylinder. We then take that cylinder and put it through a spheric lens to focus it to a point. The point where it's most focused is 18.4 millimeters from that point, so we had to make sure that the needle was exactly at that area. So the mechanical loading equipment is...
So basically, this is all the points that we created in CAD software's Autodesk and SolidWorks. So we'll split into the handle, the collimating compartment, the lens, the motor lock compartment, and the needle locator. So basically, this is the part that I worked on. So basically, I based it on handheld for dental. It's a curing light. Basically, I took pictures, put it into Autodesk, modeled that, then I imported it into SolidWorks, and designed it from that. And so once I had the handle part, we got to the Lord's collimating tube part. It was on the end, as you can see there, his part goes on. So we basically just made some slides on interference fit there.
So here we have the collimator compartment. So this housed the collimation tube, which took the laser diode straight line beam and made it into an ellipse. So the collimating tube would go into this circular compartment, and the key thing about this was that it had to be extremely tight with tolerances to assure that the center of the dot would be right at the center of exit, where the other part would connect, to assure that everything was perfectly lined up in the centric so that the beam would actually be aimed towards the inside of the needle. We had the lens compartment lure lock. So here, this part is where it attaches to the previous component we just spoke about. And then the spheric lens would be tightened through this threading, and the distance between this line here and the actual hole where the needle would go had to be that 18.4 millimeter distance to ensure that the focal point where the diameter is smallest would actually enter inside the needle. This little hole here would be where the next component would attach, which would be the needle locating the actual, or the final part locating the actual needle to the piece. And then there was the threading, which was the fastening mechanism for the actual needle that would be attached. So this is the needle locator. So here we have a diameter of 0.6 millimeters, which is the outside diameter of the needle we would be using, 0.7 gauge. So this was mainly used to assure that once the needle was threaded on, that the actual entrance was exactly where it needed to be. When you're speaking with about 1 to 200 microns diameter, this has to be extremely, extremely accurate. So this is the assembly and what it looks like. So this would be the collimating tube, which would be inserted in there, making sure that there's no leeway for it to move around at all, and it's fastened by this ring. The distance between the actual spheric lens and the collimating tube wasn't too big of an issue because the beam coming out of the collimating tube was collimated, so it didn't really diverge too much based on the distance. But the distance between the exit point and where the tip of the funnel ends, that was the really crucial part. Because as soon as that's either, if that's either too short or too long, you're getting a completely different diameter. And this is how it works. So basically, like I just said, the collimated beam would come out of the collimator, be focused down through the lens and into the funnel, and then the needle would be attached at this point, ensuring that the beam goes right out from the needle.
Testing. So testing, we broke it up into the electrical and the optical parts. So for the electrical, I used an oscilloscope. This was to measure the pulsation, the frequency, as well as I took a measurement of the max voltage. So I connected the oscilloscope to the positive side of the diode, and then just the other side of the ground. So as you can see there, I don't know if you can really see that, but right there is a frequency of 976 hertz, so just under 1 kilohertz, and here is a voltage of 2.53 volts.
So for the optical testing, it was quite